Long before dinosaurs ever appeared, Earth belonged to strange predators that almost no one remembers today. Within the darkness of deadly swamps and vast primordial forests, life was experimenting with the first true killing machines on land. Some possessed teeth as long and sharp as blades. Others carried bodies that seemed half reptile, half mammal. As though evolution itself had not yet decided what they were supposed to become. But even before them, the ancient oceans had already given birth to the planet's first monsters. Around 560 million years ago, the Ediacaran oceans were darker, less oxygenated, and almost devoid of complex biological activity. Atmospheric oxygen concentrations were only about 10 to 15%, compared to over 20% today. There were no roars, no high-speed chases, only cold seafloors covered in microorganisms and strange soft-bodied organisms drifting slowly through the water. One of the most astonishing discoveries was found in Charnwood Forest in 2022, a creature called Ororallamina attenboroughii. Standing roughly 20 centimeters tall, it resembled modern marine polyps, anchoring itself to the seafloor through a rigid stalk-like structure. But the truly terrifying part existed above it. Tentacles designed to capture plankton and smaller life forms drifting through ocean currents. Why did predation emerge so early? For billions of years during Earth's early history, life existed mainly as bacteria and extremely simple organisms. But the moment animal bodies began becoming more complex, developing tissues, tentacles, and the ability to sense their environment, evolution immediately created competition. At the time, the Ediacaran oceans possessed almost no complex food webs. There were no vast schools of fish or enormous coral reefs. But the appearance of primitive predators like Ororallamina revealed something deeply unsettling. From the very beginning, evolution had already discovered how to exploit other living things in order to survive. In such a brutal environment, any organism capable of hunting even slightly more efficiently gained an enormous survival advantage. And then everything began changing faster. Soft-bodied creatures gradually evolved protective structures. Organisms started sensing light, vibrations, and movement. Only around 20 million years after the time of Ororallamina, an extremely short period on the geological timescale, Earth entered an event many scientists describe as the most explosive burst of biological creativity in the history of life, the Cambrian explosion. For the first time in Earth's history, fast-moving predators equipped with eyes, hard armor, and biological weapons began appearing throughout the oceans. And the first evolutionary arms race of life had officially begun. Around 538.8 million years ago, Earth entered a period scientists now call the Cambrian explosion. In less than 20 to 25 million years, nearly all the fundamental body designs of modern animals appeared simultaneously within the fossil record. For the first time in the history of life, eyes became widespread. Hardened armor began evolving. The slow, soft-bodied organisms of the Ediacaran world gradually disappeared, replaced by creatures capable of accelerating, evading, and pursuing prey. One of the most famous predators of this era was Anomalocaris. Its name means strange shrimp, but the reality was far more terrifying. Reaching nearly 1 meter in length, enormous by Cambrian standards, Anomalocaris possessed compound eyes containing around 16,000 lenses, making them among the most sophisticated visual systems of the ancient world. While most organisms could only sense faint changes in light, it could already detect movement and track targets through murky water. For decades, scientists believed Anomalocaris crushed trilobites using immense bite force. But modern biomechanical simulations suggest its mouth may not actually have been strong enough to break thick mineralized shells. That discovery revealed something unexpected. It may have specialized in hunting soft-bodied, fast-moving prey, behaving more like a modern high-speed shark predator than previously imagined. Fossils discovered in China revealed the existence of Omnidens amplus, a predator reaching roughly 1.5 meters in length and possibly one of the largest hunting animals of the Cambrian seas. And then the pressure of predation began reshaping the entire planet. Trilobites evolved thicker armor. Paleontologists refer to this period as the Cambrian arms race, the first evolutionary arms race in the history of life. Predators forced prey to evolve, and prey evolving forced predators to become even more powerful in return. That conflict itself may have accelerated biological complexity at a speed never seen before. But the Cambrian period was only the beginning. Soon, creatures the size of modern crocodiles would emerge and dominate Earth's oceans long before sharks ever appeared. Before sharks became the symbol of terror in the oceans, what ruled the seas? Around 470 to 430 million years ago, during the Ordovician and Silurian periods, Earth entered an era when the oceans no longer belonged to small creatures alone. And as ecosystems became richer in energy, predators began evolving into true monsters. The oceans of this period contained enormous quantities of plankton, forming the foundation for countless marine animals. And within those dark, murky environments, gigantic predators began emerging from the shadows. One of the most terrifying creatures was Endocerus giganteum, an ancient relative of modern squid and octopuses. The fossilized shell alone measured roughly 3 meters long, while the entire body may have reached lengths of up to 5.7 meters. Imagine an ocean where sharks, whales, and large bony fish did not yet exist. In that world, Endocerus stood as an almost absolute apex predator. With its long torpedo-shaped body, it could hover silently in the water before diving downward from above to ambush smaller creatures. Some hydrodynamic studies suggest its elongated shell stabilized vertical movement through the water column, transforming it into an extremely efficient deep-sea hunter of the ancient oceans. But evolution continued experimenting with designs even more terrifying. This became the age of the gigantic sea scorpions, the Eurypterids. Pentacopterus decarahensis measured around 1.7 meters in length and was among the oldest Eurypterids ever discovered. Later came Acutiramus, stretching beyond 2.1 meters, armed with massive predatory claws capable of trapping prey within murky water. But the true peak of these creatures was Jackalopterus rhenanii, a monster that may have reached between 2.3 and 2.6 meters long. Its front claw alone exceeded the length of a human arm. Scientists believe Jackalopterus possessed excellent vision and specialized in ambush hunting within low-oxygen brackish waters. The swamps where it hunted were almost permanently darkened by mud and decomposing organic material. But within the darkness of the Devonian oceans, vertebrates began evolving stronger jaws, faster muscles, and more agile predatory abilities than anything that had existed before them. And for the first time in history, the bone-backed killers were preparing to seize control of the seas. Around 419 to 359 million years ago, Earth entered the Devonian period, often called the Age of Fishes. But this was not simply an era when fish spread throughout the oceans. This was the moment vertebrates transformed into fully realized killing machines for the first time in history. The first massive coral reef systems in Earth's history flourished, stretching for hundreds of kilometers. Marine life became more crowded than ever before. Jawed fish evolved rapidly. Some species began hunting in groups, accelerating suddenly and using bite force rather than merely grasping or crushing prey with external structures. The oceans had become a true three-dimensional battlefield, and dominating those dark blue waters was Dunkleosteus torelli, an armored monster reaching lengths of up to 4.1 meters and weighing nearly 1 ton. Its head and chest were covered in thick, bony plates resembling the armor of a tank. But the most terrifying feature was not its size. It was its mouth. Dunkleosteus did not possess true teeth like modern sharks. Instead, its jawbones evolved into razor-sharp cutting blades. Biomechanical simulations suggest its bite force may have exceeded 7,400 newtons, comparable to the bite of a modern hyena and powerful enough to pierce the armor of many ancient fish species. For many years, Dunkleosteus was imagined as a slow-moving living tank. However, modern hydrodynamic models indicate its body possessed a tuna-like form similar to modern tuna or mako sharks. During the same period, other vertebrate predators also began appearing. Megamastax amblyotus exceeded 1 meter in length and possessed an unusually powerful crushing dentition. This suggests vertebrates were no longer hunting only soft-bodied organisms. They had begun exploiting prey protected by hard shells and heavy armor as well. And there, within the oxygen-rich world of the Carboniferous period, surrounded by colossal forests, The first true kings of land predation were preparing to emerge. Long before dinosaurs ever appeared, Earth belonged to predators far stranger, larger, and, in some ways, even more terrifying than modern imagination can easily comprehend. Around 359 to 299 million years ago, during the Carboniferous period, the planet entered a unique biological state. Atmospheric oxygen levels reached approximately 30 to 35%, far higher than today's 21%. Imagine a world where forests taller than 30 meters blocked out the sky, allowing sunlight to penetrate only as faint beams through layers of dense vegetation. Beneath them spread enormous swamp systems filled with stagnant water, rich in oxygen but poor in light. This was not a peaceful environment. It was a dense network of survival where every movement could become a signal to a predator nearby. One of the creatures dominating these waters was Archaeopteryx megacephalus. Measuring around 1.5 to 2 meters long, Archaeopteryx possessed a skull nearly 60 centimeters wide, sharp conical teeth, and a heavy body resembling that of a modern crocodile. It was not the fastest hunter, but it was among the most efficient. Lurking beneath mud, waiting for prey to approach before striking with sudden force and crushing jaws. But even more terrifying were the true super predators of the swamps. Mastodonsaurus possessed a skull reaching nearly 1.5 meters long, one of the largest skulls ever evolved by an amphibian. At an even more extreme level stood creatures such as Prehistoric plumeri, estimated to reach lengths of 8 to 9 meters. That made it longer than many crocodile species alive today. With a body stretched out like a living boat, Prehistoric resembled an ancient river monster, moving slowly but becoming extraordinarily dangerous the moment it attacked. And it was not only amphibians dominating this world. The Carboniferous was also an age of extreme predatory designs. Rhizodus hybridi may have reached lengths of up to 7 meters, making it one of the largest freshwater predatory fish ever discovered. Meanwhile, Orthocanthus possessed an eel-like body nearly 3 meters long, perfectly adapted for murky, mud-filled waters. And perhaps the strangest truth of all was this: no single perfect design survived forever. Each species represented an evolutionary experiment. At that time, Earth resembled a colossal laboratory where evolution tested every possible form of predation. But within this swamp-filled world, another critical transition was beginning. Vertebrates were gradually adapting more successfully to dry environments. New body structures emerged, stronger limbs, more efficient lungs, and greater mobility on land. And from this point forward, a new evolutionary branch slowly began escaping its dependence on water, opening the path for predators with increasingly mammal-like forms to rise. Throughout the Carboniferous and early Permian periods, Earth possessed no single formula for what a predator should be. And that reality created one of the strangest eras in the history of life. An age of extreme predatory designs that sometimes seemed as though they belonged to another planet entirely. Let us begin with a creature that lived nearly 40 million years before the first dinosaurs, Dimetrodon. Measuring roughly 4.6 meters long, Dimetrodon was not a dinosaur at all, but part of an evolutionary branch more closely related to mammals. It possessed clearly differentiated teeth, front teeth for gripping prey and rear teeth for slicing flesh, a characteristic remarkably similar to modern carnivorous mammals. Scientific hypotheses suggest it may have regulated body temperature by absorbing or releasing solar heat, or perhaps functioned as a biological display structure for species recognition. Although its exact purpose remains debated, it reveals something important. Evolution does not merely optimize, it experiments. And Dimetrodon was only the beginning. Within the Permian world, even more terrifying predators emerged. Gorgonopsids became one of the earliest hunting groups to evolve saber-like canine teeth. These fangs were not designed for chewing, but for piercing deeply and killing prey quickly. This marked a major shift in predatory strategy, from grip and crush toward precise and rapid execution. During the same era, Inostrancevia reached lengths of 3 to 4 meters, armed with canine teeth exceeding 12 centimeters long, comparable to many modern big cats, yet mounted on the body of an ancient reptile-like predator. It became one of the first true apex predators of terrestrial ecosystems, capable of killing herbivores even larger than itself. And at the extreme peak of the Permian stood Antilosaurus magnificus. Some analyses suggest its bite force may have been strong enough to crush the thick bones of large prey animals. It may have been one of the largest land predators to exist before the age of dinosaurs. But what matters most is not size alone. It is the sheer diversity of designs. The Carboniferous and Permian periods did not create a single, perfect super predator. Instead, they produced countless evolutionary experiments. Some species relied on dagger-like fangs. Others depended on massive bodies and crushing force. Some optimized speed and reflexes. Others evolved elaborate display structures as survival tools. Scientists sometimes describe this as an evolutionary experimentation phase, a period of intense biological experimentation where every branch of life represented a different solution to the same problem. How to become the most efficient predator possible. And when Earth entered one of the greatest catastrophes in its history, most of these extraordinary designs would vanish almost completely, clearing the path for a new world. One where the dominant predators would no longer be amphibians or synapsids, but survivors forged in the aftermath of planetary disaster. Earth was not only once ruled by predators, It was once torn apart by the collapse of life itself. The Permian Triassic extinction event occurred around 252 million years ago. Geological studies indicate that during this period, massive volcanic activity within the Siberian traps continued for hundreds of thousands of years, releasing an estimated tens of thousands of gigatons of carbon dioxide into the atmosphere. Global temperatures rose by approximately 5 to 10 degrees Celsius, enough to destabilize the entire climate system of the planet. What happens when the oceans begin to suffocate? Within the Permian oceans, oxygen depletion, known as anoxia, spread so extensively that more than 70% of shallow marine environments became incapable of sustaining complex life. At the same time, geochemical studies indicate rising levels of hydrogen sulfide, a toxic gas capable of escaping from the seafloor into the atmosphere within biologically dead regions. An estimated 90 to 95% of marine species disappeared. This was not evolution. This was systemic collapse. On land, roughly 70% of animal species also vanished. But perhaps the strangest part came afterward. Over the next several million years, the planet entered the early Triassic period. One of the earliest predators to emerge was Proterosuchus, measuring around 3 to 4 meters long, with a downward curving crocodile-like snout specialized for hunting weakened survivors. Then came Erythrosuchus, reaching nearly 5 meters in length and becoming one of the first apex predators after the extinction event. Meanwhile, beneath the oceans, Symbospondylus youngorum emerged, growing to lengths exceeding 17 meters, among the largest marine creatures of the early Triassic world. And even more remarkably, Thalattopithecus evolved flesh-ripping hunting strategies, revealing that the oceans did not require long to recreate apex predators once again. New biological designs emerge, not because the world is stable, but because it has become too chaotic for older forms to survive. Within that post-apocalyptic silence, a new law slowly emerged. It is not the strongest species that survives. It is the species capable of adapting fastest to emptiness. And from this erased world, a new chapter was about to begin, one in which the survivors would lay the foundation for the age of dinosaurs. Around 252 million years ago, Earth emerged from the Permian Triassic extinction event like a biological wasteland, where more than 90 to 95% of marine species and roughly 70% of terrestrial species had vanished. During the early Triassic period, global temperatures remained abnormally high, fluctuating by roughly 10 to 15 degrees Celsius above modern averages in many regions, while atmospheric oxygen levels had still not stabilized. Ecosystems now resembled a blank map, little competition, countless ecological vacancies, and evolution beginning to accelerate like an algorithm no longer constrained by limits. One of the first survivors to emerge was Proterosuchus, measuring around 3 to 4 meters long. It carried the traits of a primitive biological design, a downward curving snout adapted for scavenging carcasses and hunting weakened survivors. Soon afterward came Erythrocecus, one of the largest predators of the early Triassic world. Reaching nearly 5 meters in length and possessing a skull weighing dozens of kilograms, it was powerful enough to crush smaller reptiles with ease. In the oceans, evolution advanced even further. Symbospondylus youngorum grew beyond 17 meters in length, becoming one of the largest marine animals ever to appear only a few million years after the global catastrophe. And at the very top of the ancient marine food chain, Thalatoarchon evolved flesh-ripping hunting strategies, a clear sign that fully developed food chains had already reassembled themselves. Long before dinosaurs appeared, Earth was home to a completely different kingdom of predators. Dominating the top of the food chain for tens of millions of years across the harsh supercontinent of Pangaea, these ancient creatures represented the evolutionary peak of their age. Yet the history of life reveals a brutal rule: dominance is never permanent. Their fall was not an ending, but an inevitable clearing of the path, leaving behind ecological voids for the age of dinosaurs to rise. Every peak of power is only a brief moment within the indifferent current of evolution. In the skies of Earth, roughly 320 to 300 million years ago, a shadow skimmed across the surface of a swamp, its wingspan nearly as wide as that of a modern seagull. It was Meganeura, an aerial predator that lived in the late Carboniferous and early Permian. Around 305 to 295 million years ago. Its wings stretched approximately 70 to 75 centimeters across. Fossils discovered in France and England reveal wing structures strikingly similar to those of modern dragonflies, yet on a scale far beyond any insect alive today. What allowed an invertebrate to take flight at such size? Modern physiological models suggest that the maximum body size of insects is closely tied to the partial pressure of oxygen in the atmosphere. Meganeura was not alone. On the damp forest floor, a creature as long as a small boat moved slowly across layers of decaying leaves. This was Arthropleura, a giant arthropod that lived from the late Carboniferous into the early Permian. Fossil trackways found in Scotland and North America indicate lengths reaching 2 to 2.5 meters and widths approaching 50 centimeters. Its segmented body carried a pair of sturdy legs on each segment. Imagine the ground trembling faintly beneath hundreds of synchronized steps. By the late Carboniferous, terrestrial vertebrates were still relatively small. Amphibians dominated moist environments, while true reptiles had only begun to appear. Studies of fossilized stomata and wildfire modeling further indicate that elevated oxygen levels increase the frequency and intensity of fires. This created ecosystems constantly oscillating between rapid growth and renewal after burning. Yet as the Permian began, oxygen levels gradually declined, possibly dropping to around 15 to 17% by the late period. At the same time, the climate grew drier, and reptiles better adapted to hot, arid conditions diversified. Before sharks and whales came to dominate the oceans, the seas belonged to creatures with compound eyes composed of tens of thousands of lenses, and to sea scorpions stretching nearly 3 meters in length. In the ancient oceans, a realm where life experimented with forms even more bizarre and formidable than those on land. Long before dinosaurs walked on land and giant insects filled the skies, life had already experimented with its strangest forms beneath the sea. More than 500 million years ago, during the Cambrian period, the oceans belonged to creatures whose body structures were utterly unlike anything in today's world. A shape 30 to 40 centimeters long glided over the sandy seafloor. This was Anomalocaris, one of the earliest apex predators in the history of life, living approximately 518 to 480 million years ago. Fossils discovered in the Burgess Shale reveal a body length of about 38 centimeters. Most astonishing were its compound eyes, each containing up to roughly 16,000 lenses. Modern dragonflies may have around 30,000 lenses. But during the Cambrian, such complex visual systems represented a dramatic evolutionary leap. Keen eyesight allowed Anomalocaris to detect prey in murky waters and compete in increasingly intense ecological battles. What triggered that explosion? Rising oxygen levels in the oceans, shifts in marine chemistry that enabled larger and more complex bodies to form, and increasingly dynamic ecosystems with clearer food chains. Along the seafloor, another group of organisms moved slowly through the sediment. Trilobites, for nearly 270 million years, from about 521 to 252 million years ago. They thrived and diversified throughout ancient oceans. One of the largest species ever discovered is Zodilus rex. Reached lengths of approximately 72 centimeters. Trilobites were not apex predators, but they became vital biological markers, and their diversity allows geologists to determine the ages of rock layers with remarkable precision. During the Silurian and Devonian periods, roughly 430 to 360 million years ago, the oceans gave rise to giant sea scorpions, Eurypterids. The largest known species, Ecological, may have reached lengths of about 2.5 to 2.8 meters, based on fossilized claw fragments found in Germany. In the Devonian, often called the Age of Fishes, armored fish and jawed vertebrates began to emerge and diversify. The seas, once ruled by arthropods and mollusks, operated under ecological rules very different from those of today. With body plans and survival strategies, we now reconstruct only through fossils. Complex marine ecosystems grew increasingly fragile as Earth moved into the Permian, a time when arid climates and global carbon disruptions would set the stage for the greatest mass extinction in the history of life. We return now to the supercontinent Pangaea, a world turning toward extreme heat and dryness, where new monsters would arise on a planet edging closer to the brink of annihilation. The Permian period, spanning roughly 299 to 252 million years ago, was a time when nearly all of Earth's land masses had fused into a single supercontinent, Pangaea. The heart of Pangaea became a gigantic furnace in the summer and bitterly cold in the winter. Desert sediments and evaporite salt deposits provide evidence that large portions of the Permian world experienced arid climates. Seasonal temperature swings may have been extreme. On that hot, dry terrain emerged a creature with a striking sail rising from its back. This was Dimetrodon, measuring approximately 3 to 4.5 meters in length and living during the early Permian. Dimetrodon is often mistaken for a dinosaur, but it was actually a synapsid, part of the evolutionary lineage that would eventually lead to mammals. The sail of Dimetrodon consisted of elongated bony spines extending from the vertebrae, covered by a thin membrane of skin. In a world defined by extreme temperature fluctuations, the ability to regulate body heat offered a critical survival advantage. Reptiles, equipped with amniotic eggs and less permeable skin, gradually gained dominance on land. Plant life changed as well. The dense swamp forests of earlier eras declined, replaced by gymnosperms such as ancient conifers and seed ferns, better adapted to dry conditions. Carbon isotope records from Permian rocks indicate that the global carbon cycle was becoming unstable. Above these shifting foundations stood predators like Dimetrodon. By the late Permian, around 252 million years ago, multiple geochemical indicators began shifting abruptly. Carbon isotope values dropped sharply, a signal that vast amounts of light carbon were being released into the atmosphere and oceans. Global temperatures rose rapidly. Ocean waters developed widespread zones of oxygen depletion. These upheavals were driven by processes deep within Earth's interior, where immense volumes of magma were accumulating beneath the crust of Siberia. The Permian world, already harsh and arid, was approaching a turning point. Dimetrodon and many early Permian therapsids would not live to witness that final catastrophe. Yet their distant descendants would endure the darkest chapter in the history of life. And what was about to unfold was not merely an ecological crisis. It was the greatest mass extinction in Earth's 4.5 billion year history. In the next chapter, we will witness the Permian Great Dying, when approximately 96% of marine species and 80% of terrestrial species vanished, and the planet came perilously close to losing complex life altogether. Imagine standing on the supercontinent Pangaea about 252 million years ago. The air is dry and scorching, the sky dimmed as if veiled behind a vast curtain of smoke. And to the north, in what is now Siberia, the Earth begins to split open with colossal fractures. There, one of the most violent volcanic events in planetary history unfolds. The Siberian Traps. As temperatures increased, the solubility of oxygen in seawater declined. At the same time, warming intensified ocean stratification, with warm surface waters no longer mixing effectively with deeper layers. The result was the expansion of oxygen-depleted anoxic zones across the global oceans. Evidence from sulfur and carbon isotopes in sedimentary rocks indicates that deep waters were not only oxygen poor, but also rich in hydrogen sulfide, a toxic gas capable of escaping into the atmosphere. On land, ecosystems already fragile under the Permian's arid climate began collapsing in cascading failure. Forests vanished in many regions, soils eroded, food chains fractured. the final toll was almost unimaginable. Approximately 96% of marine species disappeared. Trilobites, organisms that had endured for nearly 270 million years, went completely extinct. Ancient corals, many brachiopods, crinoids, and other groups vanished forever. On land, roughly 70 to 80% of vertebrate species were wiped out. This was a near-total reset of the planet's ecosystems. This event is known as the Great Dying. In Earth's 4.54 billion year history, no extinction has ever reached such a scale. What happens when nearly all complex life is erased? Fossil evidence shows that after the Permian-Triassic boundary, biodiversity fell to unprecedented lows. Coral reefs disappeared for millions of years. Marine ecosystems were dominated by small opportunistic species capable of tolerating low oxygen conditions. The Permian Great Extinction ended the age of giant arthropods. Many primitive reptile groups and ancient ecosystems that had persisted for hundreds of millions of years. Which organisms were capable of enduring a planet that seemed to be poisoning itself? And how did an entirely new biological order begin to emerge from that ash and devastation? Between approximately 252 and 247 million years ago, Earth's atmosphere contained extraordinarily high levels of carbon dioxide. Climate models and carbon isotope analyses indicate that concentrations may have been 5 to 8 times higher than pre-industrial levels. And there was no permanent ice at either pole. Far from the oceans, where moisture could no longer moderate temperature, the continental interior became vast, searing deserts. Studies of fossil spores and pollen reveal that vegetation collapsed dramatically after the Permian-Triassic boundary. Dense forests vanished across many regions. In their place appeared small, drought-resistant pioneer plants. And one name appears again and again in the fossil record: Lystrosaurus, measuring roughly 1 to 2.5 meters in length. It had a stocky body, a turtle-like beak, and 2 small tusks projecting forward. Yet the remarkable fact is this: at many early Triassic fossil sites, Lystrosaurus accounts for as much as 60 to 70% of all terrestrial vertebrate specimens. Paleontologists describe this phenomenon as a disaster taxon. a species that proliferates after catastrophe because it can endure extreme conditions. Low oxygen, intense heat, and scarce food. In the oceans, coral reefs had still not recovered. Marine ecosystems were dominated by small organisms capable of tolerating oxygen-poor conditions. Geochemical evidence from early Triassic marine rocks shows that many regions remained in a state of anoxia. Prolonged oxygen depletion lasting millions of years after the catastrophe. In addition, high temperatures reduce the solubility of oxygen in seawater, making it difficult for large marine organisms to thrive. If you were to stand on an early Triassic plain, you would not hear the layered chorus of hundreds of bird and insect species as you do today. The distant ocean would no longer shimmer with vibrant coral reefs, but instead stretch out in murky, oxygen-poor waters. And so, while Lystrosaurus dominated the land in monotonous abundance, somewhere in the shadows, new reptilian lineages were beginning to diversify. They were small, agile, and well adapted to the hot, dry climate of Pangaea. The early Triassic was not an age of grandeur. It was a proving ground for new evolutionary lines. Soon, we will witness the rise of those successors, the era of the monsters, before the true age of dinosaurs officially begins. As the Middle Triassic gradually unfolded, Earth began to shift its rhythm, and ecosystems were no longer as monotonous as they had been in the time of Lystrosaurus. Food webs grew more complex, and the ecological niches left vacant after the Great Extinction were now being claimed by new contenders. On land, an ancient group of reptiles rose to prominence. The archosaurs, the evolutionary branch that would eventually give rise to crocodiles, dinosaurs, and modern birds. What made them so successful? One of the most formidable predators of this era was Proteasuchus. Measuring roughly 4 to 6 meters in length and nearly 2 meters tall when standing upright. It was not a dinosaur, but a member of the Rauisuchians. With a massive skull lined with dagger-like teeth and powerful hind limbs, it could rear up on its back legs when attacking prey. Imagine standing on a Triassic plain, where vegetation is sparser than modern forests, dominated by ferns, ancient conifers, and cycads. Fossils of Proteasuchus discovered in North America, particularly in present-day Texas, indicate that it was among the largest terrestrial predators of the late Triassic. After millions of years of biologically impoverished seas, marine reptiles began to flourish. One of the most successful groups was the ichthyosaurs, reptiles that had returned to the ocean. Early Triassic ichthyosaur species measured about 1 to 3 meters in length. But by the Middle Triassic, some exceeded 10 meters. They gave birth to live young rather than laying eggs on land. Fossils of pregnant individuals have been discovered, with embryos preserved inside the mother's body. Clear evidence that they were fully adapted to life in the ocean. At the same time, shallow coastal waters were the domain of Nothosaurus, measuring approximately 3 to 4 meters in length, with a slender body, elongated neck, and sharp teeth, hunting fish and mollusks in the lagoons along the shores of the Tethys Sea. If you were to dive into a Triassic sea, you would encounter marine reptiles with blade-like teeth, cold eyes, and ghost-like movements through the water. If archosaurs and Rauisuchians dominated the land, and ichthyosaurs ruled the oceans, where were the dinosaurs? They were present, but small, overshadowed in a world filled with predators larger and more powerful than they were. One of the earliest known representatives is Eoraptor, discovered in the Ixigualasto Formation of Argentina. Eoraptor lived approximately 231 to 228 million years ago. It measured only about 1 meter in length and weighed roughly 8 to 10 kilograms. If you encountered it in a Triassic landscape, you likely would not suspect it to be the ancestor of Tyrannosaurus or Triceratops. It was slender, with long hind legs built for agility. Its small skull carried sharp teeth, suited for feeding on small prey or insects. Early dinosaurs possessed a distinctive hip structure with an open femoral socket, allowing their legs to stand fully upright beneath the body. Most large predators belong to Rauisuchians and other archosaurs, and the dominant large herbivores were not dinosaurs either, but members of older reptilian lineages. Another example is Herrerasaurus, measuring approximately 3 to 6 meters in length and living alongside Eoraptor in South America. Herrerasaurus was a swift predator with curved, razor-sharp teeth. Though larger than Eoraptor, it still faced intense competition from other archosaur predators. Analysis of fossilized bone tissue suggests that many dinosaur species grew relatively quickly compared to typical reptiles. This implies a higher metabolic rate, possibly closer to warm-blooded animals than to fully cold-blooded reptiles. If you stood on a late Triassic plain, you would witness a diverse world. Large archosaurs moving deliberately across the land, the first flying reptiles, pterosaurs, gliding overhead, and marine reptiles hunting offshore. And at your feet, perhaps an eoraptor would slip quietly past in search of food. Some would evolve into small herbivores, others into swift predators. Around 201 million years ago, Earth prepared for another major geological upheaval. Pangaea began to fragment, and massive magma activity erupted along what would become the Atlantic Ocean. The archosaurs that once dominated terrestrial ecosystems would vanish from the fossil record. Rauisuchians went extinct, and ecosystems were reshaped yet again. Dinosaurs did not begin as rulers. They began as persistent survivors in a volatile world. In the next chapter, we will explore the late Triassic geological turning point that opened the door for dinosaurs to step into their era of dominance. Around 201 million years ago, deep within the mantle, magma began to rise beneath Earth's surface. Vast fractures stretching thousands of kilometers tore through the crust. This marked the birth of the Central Atlantic Magmatic Province, one of the largest magmatic provinces ever to exist. Its estimated area exceeded 11 million square kilometers, spanning what is now eastern North America, northwestern Africa, western Europe, and northeastern South America. The eruptions did not occur in a single day. According to uranium, lead isotope data from zircon crystals in basalt, they lasted approximately 600,000 years. The total volume of erupted lava is estimated at more than 2 to 3 million cubic kilometers. Imagine enough lava to blanket the entire United States beneath a layer of rock over a kilometer thick. What truly reshaped the planet was not only the lava, but the gases. Thousands of gigatons of carbon dioxide released into the atmosphere. Studies of sediment cores and carbon isotopes suggest that atmospheric carbon dioxide concentrations may have doubled or even tripled within a geologically brief interval. global temperatures rose by approximately 3 to 4 degrees Celsius, potentially even more at higher latitudes. The oceans absorbed much of that carbon dioxide, becoming more acidic, and marine organisms with calcium shells. Ammonoids and ancient corals began to decline. On land, many archosaur groups that had competed with dinosaurs, particularly Rauisuchians and Phytosaurs, vanished entirely. Why were they unable to endure? We see traces of this catastrophe in the red rock layers of Morocco, in the basalt flows of Nova Scotia, and in sedimentary deposits in England. Before this event, dinosaurs represented only a small fraction of terrestrial vertebrate communities, with late Triassic fossils indicating they accounted for less than 5% of individuals in many ecosystems. But perhaps more important than any single adaptation was the element of evolutionary chance. When ecosystems collapse, survival does not necessarily favor the strongest. It favors those best suited to the new conditions. The lava flows of the Central Atlantic Magmatic Province also marked something else: the beginning of Pangaea's fragmentation. Those magma-filled fractures became the seeds of the modern Atlantic Ocean, which began as geological rifts during this moment of planetary upheaval. Without that magmatic event, dinosaurs might have remained a minor lineage, living quietly at the margins of ecosystems. Without the vast ecological void created by extinction, there would have been no later giants like Allosaurus or Brachiosaurus rising to dominance. Before us stretches a shadowed swamp world, thick with mist, the air heavy with moisture, the ground soaked in mud and layers of decaying plant matter. Lepidodendron rose between 10 and 40 meters tall, with trunks reaching up to 1 meter in diameter. Their bark was covered in scale-like patterns, resembling the skin of some ancient creature. Beside them stood Sigillaria, approximately 20 to 25 meters high, its trunk straight as a stone pillar, leaves clustered only at the crown. The Carboniferous climate was warm and humid near the equator. Heavy rainfall throughout the year sustained vast swamplands. When these massive trunks fell, they did not fully decompose. At that time, bacteria and fungi capable of efficiently breaking down lignin had not yet evolved. Over time, under increasing pressure and temperature, the buried plant matter transformed into coal, Many of the world's largest coal deposits today, from Europe and North America to Asia, trace their origins to the Carboniferous period. Geochemical evidence from sulfur isotopes and atmospheric modeling suggests that oxygen levels rose from about 15% at the beginning of the period to nearly 30%, possibly reaching 30 to 35% by the late Carboniferous. Compared to today's 21%, this was an extraordinary difference. An oxygen-rich atmosphere made wildfires easier to ignite and far more intense. Fossilized charcoal from this period appears frequently in sedimentary layers, confirming that fire was a regular component of these ecosystems. Yet elevated oxygen did more than fuel flames. It reshaped biology itself. As insects and arthropods breathe through a network of air tubes known as tracheae, which deliver oxygen directly into body tissues. It was a feedback loop. Biosphere and atmosphere entwined in a chemical dance lasting millions of years. Then, as the swamplands began to shrink toward the end of the Carboniferous and the Permian approached, the climate grew drier, the giant forests declined, oxygen levels began to fall, and the stage shifted. We are about to enter the world of giant insects and arthropods, where atmospheric chemistry transformed small organisms into the true monsters of the age before dinosaurs. Earth before the age of dinosaurs was not a quiet prelude, but a planet of extremes, where life was forged in the crucible of geological and chemical upheavals on a catastrophic scale. From the assembly of the supercontinent Pangaea to the severe fluctuations in oxygen and carbon dioxide levels, every organism, from giant insects to the earliest archosaurs, was a direct product of a planetary system in the midst of restructuring itself. The history of this era demonstrates that dominance is always temporary, governed by carbon cycles and continent-spanning magmatic activity. Devastating mass extinctions erased the old monsters. Yet at the same time cleared the ecological arena, creating space for new forms of life to rise. Dinosaurs did not simply claim the world. They inherited a planet already reshaped by the ashes of earlier collapses. In the end, the message of this prehistoric age remains a constant truth. Life never truly stops. It reorganizes, adapting to an Earth that never stands still. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, Don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.